Welcome back to Lecture 2. This is the first of our 8-lecture overview of cosmology. We're trying to construct a framework on which later lectures can build. So don't worry if things go by a little fast in these early lectures, because I'll return to almost everything later in the course. So in this first lecture, I want to remind you of the hierarchy of structures that we find in the universe: planets, stars, galaxies, galaxy clusters, and the galaxy web, saying a little bit about each. Now, in cosmology, we don't take the existence of such structures for granted, because the early universe was very smooth indeed, with none of these structures present. So one of the most important missions of cosmology is to account for how all these structures have emerged from smoothness. And as will become clear, it's the attractive force of gravity that plays the role of chief architect in the creation of cosmic structures. So let's start with planets, close to home with this lovely picture of our own planet, the Earth. One is immediately struck by its beautiful spherical shape. As promised, it's the inward gravitational force from all the matter that crushes itself into a sphere. In fact, it goes deeper than this, literally. If you took a giant knife and maniacally sliced out a section of the Earth, you'd find the insides to be stratified. Gravity's pulled the denser material down to the center, where it's further compressed by the overlying weight. Of course, there are other planets in the solar system, some similar to the Earth, like Mercury, Venus, or Mars. But others are much larger, like Jupiter, Saturn, Uranus, and Neptune. In all these, gravity makes them spherical and internally stratified. The enormous mass of the Sun also provides the gravity that keeps the planets in their more or less circular orbits. Now, planets are thought to be quite common in the universe, although actually detecting them is extremely difficult, and only about 300 planets orbiting other stars have actually been found. But nevertheless, we think that most stars have planets, mainly because they're thought to form as a natural byproduct of forming a star. Maybe 0.1% of all the mass that goes into a star ends up as planets. Of course, despite being so minor in mass, they provide one of the very few places in the universe with sufficiently tranquil conditions to allow molecules to form, and in particular, big molecules, the kind needed for life. So, while planets are an astronomical afterthought, from our perspective as sentient life forms, they're really very important objects. Let's get a quick sense of scales here. The Sun is famously big compared to the Earth. For example, with the Sun as this grapefruit, the Earth is a 1 millimeter ball, like the ball in a ballpoint pen. The Sun is about 100 times the diameter of the Earth, so it's 100 times 100 times 100, or 1,000,000 times the volume, and contains 300,000 times more mass. In this model, the Earth would be located about 10 yards away from the Sun, a distance of about 93 million miles, or 150 million kilometers, or, stated in yet another way, it takes light just 8 minutes to get from the Sun to the Earth. We say the Earth is 8 light minutes away from the Sun. Moving out, planets are other tiny balls spread over a few hundred yards. Neptune, for example, is 300 yards away, about 4 light hours from the Sun. Now, throughout this course, we'll be using these light travel times to measure distance. So let's just become familiar with them. They're a bit like using car journey times to refer to intercity distances. One might say, for example, New York is 6 hours from Washington, meaning it takes 6 hours to drive from New York to Washington at a typical car speed. The most famous distance of this kind is the light year, the distance light travels in 1 year. Now, in 1 second, light travels 186,000 miles, or 300,000 kilometers, or 1, 2, 3, 4, 5, 6, 7 times around the world in 1 second. So in 1 year, which is 31 million seconds, light travels nearly 10 to the 13, that's 1 followed by 13 zeros, kilometers. Back to our model with the Earth as a sphere 1 millimeter in size, a light year is now 500 miles. So from a human perspective, a light year is a very large unit of distance. But it turns out that the distances between stars near the Sun are typically a few light years. So let's now turn to consider stars, starting with the Sun. This is a gorgeous image of the Sun, taken in ultraviolet light, and it really evokes the upwelling of energy from the deep interior. Once again, here's the Earth, which by comparison is tiny. Let's again slice open the Sun to look inside, and as before, we find the enormous weight of the outer layers pushes down to make a highly compressed core. In fact, the weight is so great that the central pressure, and in particular temperature, is high enough to cause atomic nuclei to combine or fuse. These thermonuclear fusion reactions release energy. So there is effectively a furnace burning at the center of the Sun. The heat from that furnace rises, quietly at first, and then through turbulence and convection, and it eventually comes to the surface and heats it. Of course, hot things glow, and hence the Sun and stars shine. It's really very simple. Stars shine because the furnaces at their center make their surfaces hot. Now, as stars go, the Sun is thoroughly ordinary. It's mid-sized, it's mid-mass, and it's in mid-life. One sees countless stars out in the sky, and although I don't have time to explain how, it's possible to measure many of their properties. It turns out that although most stars are basically similar to the Sun, there's nevertheless quite a bit of variation. They span a range of about a factor of 1,000 in mass, from 1/10 of the Sun's mass to 100 times the Sun's mass. They span a factor of 1,000,000 in size, from Earth size to solar system size. And they span a factor of 1,000,000,000 in power, from 1/10,000th the power of the Sun to 100,000 times the power of the Sun. So they're a bit like humans. Stars are basically the same, but with some variation. Now, stars gather together by gravity into huge assemblages called galaxies. So let's now have a look at these, starting with our own galaxy, the Milky Way. This, of course, is the term we use for the band of light visible to the naked eye that sweeps across the sky. Here, seen above the Gemini telescope in Hawaii. And here, through a fisheye lens, which shows the entire hemispherical sky with the horizon all the way around the edge. Of course, we can't get outside our own galaxy, but if we could, this is what it might look like. The Sun would be located about 25,000 light years from the center, about 2/3 of the way out. And as you might imagine, from its spiral appearance, the entire system is rotating, taking roughly 200 million years to complete one rotation. Now, with an age of roughly 14 billion years, galaxies have rotated 50 to 60 times. One might say they are 50 to 60 galactic years old. Now, it's difficult to imagine just how many stars are in galaxies, so this might help. Imagine filling this large 1-meter cube with fine beach sand. 100 billion grains. That's the number of stars in our galaxy. So that's 1 for the Sun, 1 for Betelgeuse, 1 for Polaris. It would take me 3,000 years to count them all at that rate. It's also difficult to imagine how big galaxies are. So let's consider the Earth's orbit to be the size of this pinhead. The Earth is now the size of a virus, and the Sun is the size of a human cell. And the solar system is this big. The nearest star is another human cell 300 yards away. All the visible stars in the night sky are within a few miles, but the galaxy spans the entire United States, with its centre somewhere in Nebraska. Now, the take-home message here is that galaxies are big. Pinhead to the United States, Earth's orbit to the galaxy. So, what about other galaxies? Unfortunately, with the exception of one or two, they're just too faint for our eyes to see. If you could ask a nocturnal animal, an owl, for example, what the night sky looked like, they would tell you, if they could, there were points of light, stars, but also fuzzy blobs, galaxies. Of course, with telescopes, we can match and surpass nocturnal vision, and this is what we see with the world's best telescopes. Spectacularly beautiful, spiral and barred shapes, with lanes of gas and dust, with some galaxies being just big fuzzy balls of stars. Their apparent complexity does correctly reveal a complex environment in which stars are born, live and die in an ongoing cycle. Now, from our cosmological perspective, however, we will view galaxy anatomy very simply, with just three components: a central bulge, a disk with spiral arms, and a sparse halo that surrounds both. One of our goals will be to explain how the bulges, disks, and halos of galaxies are made, and why some galaxies are all bulge, while other galaxies are all disk. Let's move on to consider larger systems. As always, gravity's at work trying to pull galaxies into groups and clusters. Our own Milky Way galaxy, for example, belongs to a small group of about 30 galaxies called, rather unimaginatively, the local group. You can see some of the members here. Orbiting our own galaxy are a few dwarf galaxies, including the famous large and small Magellanic Clouds, roughly 150,000 light-years distant. And somewhat further away, about 2 million light-years, are the two beautiful spirals, M31 and M33, each with their own little entourage of dwarf companions. Now, our group is fairly sparse, but some groups can get quite dense, like the one shown here. You can tell from these images that when the galaxies get too close, their gravitational pulls on each other induce distortions, which can look quite spectacular. In fact, galaxies can and do actually collide and even merge into a single larger galaxy, as you can see in these images, with a result that is a spectacularly beautiful mess. Now, this topic of galaxy collisions will be extremely important to us because it's thought to be one of the major ways in which galaxies are first constructed and then continue to grow and mature by collisions and merging. As for the largest galaxy groups, here are some images of fairly rich galaxy clusters containing perhaps a few thousand galaxies. As you might imagine, in these rather busy environments, galaxy encounters are quite common. And this results in a systematic difference between the galaxies that live inside clusters and the galaxies that live in less crowded environments. For example, spiral galaxy disks are rather fragile things, and they tend to be destroyed in this kind of busy environment, which is why you don't see too many of them in these clusters. Now let's step back and look at the much larger distribution of galaxies out into the universe. This map shows 250,000 galaxy positions out to about 2 billion light-years, roughly 1,000 times further than our near neighbour M31, which would be invisibly close to the Milky Way here at the centre of the map. What we see is that the galaxies are distributed neither uniformly nor randomly, but they tend to make up a patchy network, including large regions of very few galaxies, called voids, and regions with many more galaxies that are in lines or sheets. The pattern is sometimes called the cosmic web. Again, one of cosmology's goals is to explain why this web-like pattern exists, as part of the overall topic of explaining the origin of all structures, stars to galaxies to clusters to the web. As I mentioned at the beginning of this lecture, gravity is the chief architect, but it needs some initial roughness to work on. As we'll see in Theme 7, we think that initial roughness was made in the Big Bang itself by inflation's launching mechanism for the expansion. This seeded the universe with slightly denser and less dense regions which, over time, have grown into the entire hierarchy of structures. It's a lovely story which we'll look at in Theme 4. Now, to look further is more difficult and is typically only done for small regions of the sky. The most famous example of this is the Hubble Deep Field, where in 1995 the Hubble Space Telescope stared for almost 10 days at a tiny patch of sky as big as a pinhead held at arm's length. It was near the Big Dipper in the sky. The resulting image contained almost 3,000 galaxies, so we can quickly arrive at the total number of galaxies currently visible. It's 3,000 times however many pinheads it takes to cover the sky, and that turns out to be about 100 billion galaxies. Now, coincidentally, that's about how many stars are in our galaxy, however many fine grains of sand will fit into our large 1-meter cube. Some of the most distant galaxies seen in the Hubble Deep Field are 12 billion light-years away, which is almost as far as it is theoretically possible to see. Now, why is that? It's because the universe is only 14 billion years old, so one cannot see further simply because there hasn't been time for light to get to us. Let's now get a feel for the scale of the entire visible universe. If the Milky Way galaxy, what I tried to persuade you was so huge, were now just 20 yards across, the size of a large classroom, then our neighbour Andromeda galaxy would be 600 yards away. All the nearby Pretty Picture galaxies are within 50 miles. The large sky surveys span 500 miles, and the Hubble Deep Field stretches almost to the visible limit, which spans the entire United States. The take-home message here is that if you thought our galaxy was big, the visible universe is very big. 20 yards to the United States is our galaxy to the visible universe. Now, this diagram has glossed over a wonderful feature of modern astronomy that arises from the fact that it takes time for light to travel to us from the remote universe. Imagine looking at a galaxy 7 billion light-years away. Its light took 7 billion years to get to us. So we see that galaxy as it was 7 billion years ago when the light set out, not as it is now. Now, that's half the age of the universe ago. So it's a bit like looking towards an 80-year-old person, but seeing them as they were when they were 40. Now, by looking further and further away, we see back to the younger and younger universe. Now, let's push this idea to its fascinating limit. What happens if we look not 7, not 10, but 14 billion light-years away? What was going on 14 billion years ago? The Big Bang. So we should see the Big Bang if we look far enough away. Now, notice it doesn't matter which direction we look in. All directions end up at the Big Bang, very far away. So we should see the Big Bang all around us at great distance. as we'll learn in Lecture 13, that more or less is what the microwave background is. We're now ready to sketch out how astronomers see the universe. Here's a sketch of the very young universe shortly after the Big Bang. And here's a sketch of the universe today. But what we witness is the following. We seem to be at the centre of a huge sphere of radius 14 billion light-years, with old galaxies nearby and ever younger galaxies further away. And at the edge of this sphere sits the Big Bang. Now, there is a potential for confusion here. This image is not how the universe currently is. This Big Bang region happened and ended 14 billion years ago. Right now, there are old galaxies sitting there. But that's not what we see because their light hasn't got to us yet. This diagram shows what we witness of the universe, not how the universe actually is. As you might imagine, though, this is a fabulous quality of nature, because one of cosmology's main aims is to uncover the history of the universe, and one can do that simply by looking far away. Let me end this lecture with a kind of review, in which we'll place all objects, from protons to the visible universe, on a single graph. This will also give me a chance to review very large and very small numbers and exponential notation. So here is an interesting graph, with size along the bottom and mass up the side. The units are metric. The units of mass are kilograms, roughly the same as this bag of flour. The units of length are meters. It's a little bit longer than a yard. Back to the diagram. It's very important to notice the divisions on these axes are exponential. They jump by a factor of 100 from one to the next. 1 meter, 100 meters, 10,000 meters. And in the other direction, 100th of a meter, a 10,000th of a meter. In this course, I'll often be using graphs with this kind of axis because it's extremely useful. It allows you to scrutinize very tiny and very huge things all at the same time. Notice I've also written the numbers in powers of 10 notation, where the power simply gives the number of zeros for big numbers or the number of decimal point shifts for small numbers. See here, 10,000 is 10 to the 4 because there are 4 zeros. And down here, 0.0001 is 10 to the minus 4 because the decimal point has been shifted 4 places. One last comment about large and small numbers. Here are their common names. So starting at 1, we go to 1,000, 1,000,000, 1,000,000,000, and 1,000,000,000,000, jumping by a factor of 1,000 from one to the next. And these also have prefixes: kilo, mega, giga, and tera. For example, 1,000,000,000 years is a gigayear. Going in the other direction to smaller and smaller numbers, we have 1,000th, 1,000,000th, 1,000,000,000th, and 1,000,000,000,000th, with prefixes milli, micro, nano, and pico. Please don't ever confuse these. A factor of 1,000 is really very significant. Here is a meter rule, and here is a millimeter, 1,000th of a meter, the ball in a ballpoint pen. So, for example, if this is 1,000,000 light years, this is 1,000,000,000 light years. And if this is a picosecond, this is a nanosecond. These are not just very big or very small numbers. They're really very different from each other. Okay, let's get back to our graph of size versus mass with exponential axes. Here are some familiar objects we can place on the graph. Each has an approximate size and mass. An insect, people, cars, whales, and so on. I've chosen the graph limits to be roughly the boundaries of our intuition. The horizon at 100 kilometers and a dust speck at 1/10 of a millimetre. Notice that all the objects lie approximately on a diagonal line. Bigger objects are, not surprisingly, more massive. In fact, they lie close to the line that is defined by the density of water. Most objects in our world lie close to this line because they're made from atoms that are packed and are touching. Now let's embed this graph in its parent graph, whose axes now span an incredible range of 50 powers of 10 in size and 90 powers of 10 in mass. Almost all of this lies outside our ability to intuit, but that's okay. Our exponential notation helps us navigate around these regions beyond our intuition. Here you can see the basic building blocks of nature: nuclei, atoms, planets and stars, galaxies, and the entire visible universe with a size of 14 billion light years, containing a mass of 10 to the 53 kilograms, or 10 to the 23 times the mass of the Sun. Graphs with exponential axes are really amazing. They can include so much. Let's look in a little more detail here. Now I've revealed a few more objects: a human cell, a mountain, the Earth, planets and the Sun. And you can see once again how things made of atoms really hug this line of atomic density. But also notice that when some stars die, their gravity can crush the atoms down onto just the atomic nuclei, making a star of pure neutrons. So here we find the line of nuclear density. Notice how it nearly touches the top left-hand corner of our human world. A piece of nuclear matter the size of a speck of dust weighs about as much as a house-sized boulder of rock. What about less dense objects? Here's the solar system, interstellar clouds, galaxies, clusters, and voids. And here's the average density of the universe, a tiny 6 hydrogen atom masses per cubic meter. As expected, voids are a little less dense than average, while galaxies and clusters are denser than average. Now, I want to end this lecture on a positive note, because throughout it, I've tried to impress on you how mind-numbingly huge galaxies and the universe are. And there is a danger that you are now feeling, both physically and emotionally, rather small and insignificant, which can be a little depressing. But this need not be the case. Size and mass are only one rather crude way to evaluate things. This final diagram tries to rank objects by their complexity. Now, I failed to find a quantitative measure of this, so this is just my guess for an exponential scale of complexity. The important thing to notice is that galaxies and stars and planets are, relatively speaking, extremely simple things compared to, for example, DNA molecules, an integrated circuit, or a human cell. In fact, on this plot, living things are enormously more complex than these astronomical objects. Here's a nice way to illustrate this. If things shone with a brightness proportional to their complexity, then galaxies and stars would be dim light bulbs, while just your brain alone would shine out like a quasar beacon, visible across the whole universe. We are special, cosmically speaking, and we can feel genuinely good about that. But let's not get too arrogant. Since an ant or a cockroach or your pet goldfish shine almost as brightly as you do.